Hello and welcome to our lesson on exponential functions. So what it means for a function to be exponential is that it has a variable exponent. And when we have the variable exponent, or the ability for the exponent to, let's say, increase infinitely or decrease infinitely, what you're going to see is growth or decay that's really quick. So we have values that are going to increase really quickly. You're going to have values that are going to decrease really quickly depending on what the base of the exponential is. So in parent form, an exponential function would be something like f of x equals some base, we'll call it b, raised to the x power. So the base is some fixed growth factor, and we'll talk about the factor portion of that in a second. But the variable exponent, again, is going to cause that growth or decay, depending on what that base is. Now, there are a couple of restrictions for the base. I know we've talked about these, but our base has to be bigger than 0. Greater than 0 definitely can't be equal to 0, and bigger than 0. If we see a negative, which would be the numbers obviously less than 0, the negative is just considered a transformation. So we want the base to be bigger than 0, and we also cannot let that base equal 1, because if we let the base be equal to 0 or equal to 1. 0 raised to any power or 1 raised to any power would produce the same output, and we would get a constant function, which is not the same behavior as what the exponential is supposed to do. Now, when the base is bigger than 1, that's when we see a graph that is going to increase exponentially, as we say. That's going to be our growth situation, and that's what we have in the first example. So in the first example, our base is 3, again, bigger than 1. So when we input our values, just to recap on how this behavior looks, right? When I go to input a negative 2, so 3 to the negative second, remember the negative exponent rule. This is really becoming 1 over 3 to the positive second, so I get 1/9 as my output. If I make this a negative 1, 3 to the negative first, that would be 1 over 3 to the positive first, which would be 1/3. Anything raised to the power of 0 is 1. 3 to the first would be 3. 3 squared is going to be 9. And again, we're going to capture here the essence of the exponential, which is hopefully a picture you already know. So at negative 2, our graph is really low down here. It's up a little higher at negative 1. Anything to the power of 0 is 1. 3 to the first is 3, and then 3 squared makes 9. And I just assumed that was 9. 3, 6, oh, I'm 1 off. 3, 6, 9, here we go. Okay, so as we continue to pick larger and larger values for the exponent, this is going to just increase faster and faster and faster. But as we go this direction, we're going to be approaching the axis here, because these values are going to get bigger, and this value of the top of the fraction is going to stay at 1, and so the value of the fraction gets infinitely small, sort of like it does with our rational functions that approach horizontal asymptotes. So there's a horizontal asymptote in this graph, but only one end approaches, the other end obviously growing toward infinity. Okay, now that's when we have a base of 3. We can see, I called that earlier a growth factor, that the values here are increasing by a factor of 3. So 1/9 times 3 is 1/3. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. Because every time we increase the exponent by 1, we're multiplying by another factor of 3. So we say that 3 represents the growth factor in that case. Okay? So that's our exponential growth, again, an increasing graph. When we have a base that's something between 0 and 1, that's when we see the graph decreasing. That's a exponential decay situation, and hopefully it will make sense. Now again, we should know this picture, but just to be sure, if let's start with the positive there, raise 1/3 to the second power, 1/3 squared, 1/3 times 1/3, that's 1/9. If I raise it to the first, I get 1/3. Anything to the power of 0 makes 1. Now 1/3 to the negative first would be 3 over 1 to the positive first, which would just be 3. And then to the negative second would be 3 over 1 to the positive second, which would be 9. So we see the outputs here flipped from the table that we just did. So as the exponents get smaller in this case, our values are going to grow, but as x gets larger, they decrease infinitely. They're going to get infinitely close to 0. So this direction, as x approaches negative infinity, our outputs, our y's, our function is going to approach positive infinity. So at -2, we're up at 3, 6, 9. And then at 1, or -1, we're at 3. Anything to the power of 0 is 1. And then we're down at a third, and then a little lower. And then this is just going to keep approaching the axis here. And again, I missed. Let me try that again. This is going to continue to grow in this direction. And this is the basic shape that we see every time we have exponential growth versus exponential decay. So the increasing values, because we are multiplying by 3, right? The decreasing values, because I'm multiplying by a third, which is dividing my values by 3. So when I am dividing those values, again, I'm making them smaller. So anytime you have a fraction here that's between 0 and 1, you're going to be making your numbers smaller because you're multiplying by some value that's going to be, cutting them by a third, cutting them by a half, and so on. So if that fraction value is between 0 and 1, again, a decreasing graph gives us that decay. So the growth factor making our function grow bigger or decrease smaller, okay? So the basic pictures, we've seen these, really nothing too earth-shattering there. Transformation rules, I don't think we talked about these in the previous module, but they still apply. So we want to be able to visualize what our function looks like and how we can apply the transformations to make a basic sketch. Again, knowing the behavior of these graphs is going to be super helpful as we move on to calculus. So for instance, if I'm looking at y equals 3 to the x plus 3 minus 1, I know what 3 to the x looks like. Just graphed that one. That's my basic exponential growth function. But in this case, I know that this is going to shift the graph to the left 3 units, and this is going to shift the graph down 1 unit. So now I need to apply those using some reference pieces here. Now I could see that when I graph this, I didn't even go through this point, but you were just going to let that slide, right? So what I like to use as a reference is my y-intercept. At the origin is the point I normally try to use as reference, but nothing's happening there for this graph, so I'm going to use my y-intercept as my reference point, and I can just shift my horizontal asymptote and the actual exponential function sort of with any shifts that I apply to that point. So instead of my graph touching the y-axis at 1, it's going to have a point that goes left 3 and down 1. So I'm going to move that particular point left 3 and down 1. So if I started here, again, that's where my function normally would cross the y-axis, and I go left 3 and down 1, that new point of reference is here. And if my horizontal asymptote was going to be at 0, then it should now be shifted down 1. So I'm going to sketch in my asymptote, and then just my branch going through that point. So something like this would be a decent sketch. Now I'm not really concerned about this point where it touches the y-axis, although if I wanted to find it, I should be able to. To find a y-intercept, you put a 0 in for x. So just quickly, again, if I wanted to, 3 to the 0 plus 3 minus 1. So that would be 3 to the third power 27 minus 1 would be 26. If I needed to, I could say, okay, this point is at 0 and 26. Now, I'm not super concerned with that, but just know that you should be able to find that if you needed to. Okay? Next one, again, I can see 3dx like the parent form there, but I have some transformations to apply. So I have this negative, and that negative is going to make the graph reflect over the x-axis. I also have a 1/2 here. It's a little bit hard to just kind of sketch, but the 1/2 is going to be a vertical compression of the graph. It's going to slow it down a little bit, if that makes sense, right? You're tripling your outputs, but then you're going to cut them in half, so it slows it down just a bit. Again, a vertical compression. Technically, we would say by a factor of a half. And then this -2 is going to make everything go to the right 2. Okay? So visualize these pieces, or these things happening one at a time. If I reflect it over the x-axis, instead of my function being here, my function would be upside down, so here, and it would be crossing at 1. But then I want to take that and I want to go to the right 1 with it. So if I go to the right 1, then I'm going to sketch my graph through that point instead. And if I just reflect and go to the right one, obviously my asymptote didn't move, so that's still there. And I want to approach this direction now, oops, because we reflected. And then I'm just going to try to draw it a little bit wider, but that's basically going to be the picture, okay? A sketch of basically what's happening so that I can, one of the major things is identify the end behaviors. Like just from the sketch, I know the left end is going to be approaching the horizontal asymptote, which is at -1, and the right end is approaching positive infinity. And over here, I can see the left end is approaching the horizontal asymptote at 0, and the right end is approaching negative infinity. Again, key things for us to be able to identify as we move. And again, one more time, if I wanted to find this y-intercept, I'd put a 0 for x and solve. Not so concerned about that, but you should be able to do it. And one last one here. Again, I see my parent, but now I have a vertical, let me put this down here, a vertical stretch of my graphs that would speed things up. So again, you have this growth factor of 3. You're tripling your your outputs every time, and now you're going to multiply those outputs by 4. It's going to make them grow even faster. So a vertical stretch happens there. I know this is going to shift everything up 2 units. And this is going to reflect our graph over the y-axis. So, okay, so normally, again, my horizontal would be at 0, but this graph is going to go up 2. So my y-intercept, which is at 1, is now going to be at 3. My horizontal, which normally is at 0, is now up at 2. And then through that point, instead of making the increasing graph, because I put that negative there, I'm going to reflect over the y-axis and make this graph decrease. So it's going to look something like this. Oh, and let me just, because this is vertically stretched, then maybe on this side I make it grow a little faster than I had drawn it in there. But again, just a sketch for me to know in this one exactly where it touches the y-axis, to know that it's not going to touch the x-axis, that the left end of the graph is going up toward infinity, and the right end of the graph is approaching the horizontal asymptote, which is now at 2. Okay? So being able to use the transformations in Sketch because you know what the parent function looks like, so important, and not overly difficult. Alright, so there's the concept there. I also want to mention for you and bring up for you y equals e to the x. If you've not seen e before, which if you're coming from college algebra, you should have. This is Leonard Euler's number. We call it Euler's number E. I know this doesn't look like Euler, but that's how his name is pronounced. It's like pi, an irrational number, which just means it's a non-repeating, non-terminating decimal. It is a very natural base for an exponential function. It's a little bit hard for me to show you here, but when you get to calculus and you start talking about limits, this can be defined in terms of limits. It basically comes from one of the easy ways to see its origins from the compound interest formula. I don't know if you remember this, but interest compounding more frequently ends up resulting in more interest earned on interest, and more frequently, again, earns you more, but there's like an infinite number of times that you can compound the interest, and as that number gets bigger and bigger and bigger, what you see is it approaching this value of e, which is 2.71828 forever, on and on and on like pi, but we're just going to say it's about 2.72. So the same way pi is a non-repeating, non-terminating decimal that goes on forever, but we just say it's about 3.14, that's what's happening here. So even though you don't know exactly where it's coming from, know for now it's just a mathematical constant. So we use pi as 3.14, we use this as 2.72, and again, it's a very natural base for us to use for exponential functions. So we should have an idea of what it looks like. If we were to graph y equals e to the x, how would it look? Pausing as if you're going to answer me. No. This is just an exponential growth function. Remember, this base, if we just said it's about 2.72, if I said graph 2.72 to the x power, it's growth because our base is bigger than 1. And so what we would see is e to the power of 0, just like anything else to the power of 0, would be 1. E to the first would be itself, which is almost 3. E squared is going to be 7 point something, so 3, 6, 7-ish, whatever up here. And on this side, we're going to end up with some decimal values that get, that was terrible, infinitely close to 0. So it's just an exponential growth function. It's just a very specific base of, but yeah, exponential growth at its core. Okay, so it still has a horizontal asymptote here, still crosses at 1. Our domain, and I don't think I mentioned this yet, but domain for all exponential functions is all real numbers because I can input anything into the exponent and an output would be produced. Though what gets restricted is the range because obviously the exponential is not going to go above or below its horizontal asymptote depending on if there's a reflection or not. Okay? So same properties as all of our other exponential growth. Now I think the more important part to our review today is going to be with some applications or exponential functions in context. But before we do those, let's just make sure we can identify exponential growth or exponential decay when we see it. So if I give you the graph of a function, you should be able to recognize it as one or the other, or neither if that's the possibility. And if I give you an equation, again, recognize its growth or decay or neither. So hopefully you're looking at this first one and recognizing this increasing graph with this horizontal asymptote is absolutely exponential growth. And I'm hoping that you're recognizing that second picture is not exponential at all. I don't see a horizontal asymptote there. What I see in that picture is polynomial behavior. So this is not exponential, right? This is a polynomial. Oh my goodness. Not exponential. This is a polynomial. Can't fit all the words, all the letters to the word in there. Okay. And graphs, I think, at this point, we should be becoming pretty familiar with. Now, let's look at some actual equations and determine. Remember, if a function is exponential, what we're looking for is a variable exponent. Once we've established it's exponential, we look at the base to see if it's going to grow or it's going to decay. So first function, our exponent here, not a variable. Even though we have an exponent, it's not exponential. That is a cubic function, so that is neither growth nor decay. Second one has a variable exponent, and because there's a 0.75 here, think about that as 3/4. Every time you multiply by 3/4, you're going to be making your number smaller. That base being between 0 and 1 means this is decay. So again, here our base is bigger than 1. Here our base is between 0 and 1. Third function, again exponential, we have a variable exponent, so we're good. The base being 1/3 means we're going to be making our values smaller and smaller and smaller. Again, that's decay. Variable exponent here, base being bigger than 1, means that's going to be representing exponential growth. I really hope we're recognizing this. That is not an exponential function, that is a linear function, so neither. And then here we have a variable exponent, base bigger than 1. Those numbers are going to double every time, so that is exponential growth. Okay? So not so bad, but again, let's now turn our attention toward some exponential functions in context. When we're dealing with exponential functions in context, we have a slightly altered parent form. We're going to look at these as y equals, or f of x equals, a times b to the x power, where the b to the x power, that piece is our exponential, right? The b is still our growth factor, but a is important. So a in our parent function is, let me just take it to Desmos for a second here. In our parent function, if we have just b to the x, then technically there's a number out there, but it's a 1, right? And that's important to know. So if I have just y equals 3 to the x, so to the x, there we go. That 1 out in front, right, gives us our parent form. If I change that to something else, and we saw a stretch a second ago, but if I make it, let's say, a 4 out in front of our 3 to the x, I think that's the one we saw earlier, then what happens is, again, the graph is stretched, but something more specific is happening. Right? Anything raised to the power of 0 is why we have this output at 1. Well, now if I raise 3 to the power of 0, but then I multiply it by a 4, my graph's going to start up there at 4. If I change this to a 6, then my graph is going to start up here at 6. And that starting point, or y-intercept, is going to be the starting point in context. Because in a contextual situation, like in a real-world problem, none of the negatives are going to apply. Everything's going to happen in quadrant 1. So if I want to know where my situation is going to start, I want to know where the y-intercept is, it has to be the coefficient of my exponential. So a represents the starting value, the initial value in your situation, which is when your x or your time or whatever it is in your situation is 0, and that again ends up being just the y-intercept. So it does still stretch our graph or compress our graph like we saw in the transformations, but specifically when we stretch or compress that y-intercept, which starts at 1, right? If we stretch that 3 times what it's supposed to be, it goes up to 3. If we cut that into half of what it's supposed to be, it gets compressed down to a half. So that's going to be our starting point in a contextual situation. B, as I've mentioned, is our growth factor. Again, it's what we're multiplying by to get from one output to the next. We saw that in those tables in the beginning. But finding b from context could be a little tricky. If I can't see what I'm multiplying by to get from one output to the next output, then maybe I divide. So to find b, I could work backwards by dividing consecutive outputs. But sometimes I'm not given consecutive outputs at all, so I can't just look at the outputs and see what am I multiplying by, or what am I, or what, divide to try to figure out what I'm multiplying by to get from one output to the next. Sometimes I'm given that there is a percent increase or decrease in a situation. Now, hopefully this will make sense. Let me go to Scratch for a second. Let's say that you buy something for $100, okay? If I said that the next year that thing was going to gain 50% of its value, 50% of 100 would be $50. So the next year this would be up to 150. And if every year it continued to do the same thing, what's going to happen? Well, the next year, if it gains 50% of its value, 50% of this one is going to be 75. So now it's going to grow by $75, which would make the next output 225. And this ends up representing exponential growth. If we grow by a percentage or if we decay by a percentage, then we are going to see exponential growth. And you can see because, maybe by the percents it's not as clear, but if I wanted to go from here to here, what am I multiplying by to go from 100 to 150? Or in reverse, if I took 150 and divided it by 100, then I end up at 1.5. So 100 times 1.5 would take me to 150. And if I multiply again 150 by 1.5, then it takes me to 225. So my growth factor is 1.5. Now I said grow by 50%, but when I see my growth factor at 1.5, that's really 150%. That's because we start at 100% of our value and we're adding 50% of that value, and that's where that number comes from. Okay, so I don't know if that makes sense, but if we are given a percent gain or a percent loss, we are looking at an exponential growth or decay situation. So to figure out the value for b, we want to take that percent increase or decrease and either add or subtract to or from 100 and then convert to a decimal. So the example I showed you was a 50% increase, but we ended up at 150% for b, and so we had to take the 50% added to 100 and then make it a decimal. 150% gives us the 1.5. And it should make sense to add it to 100 or add it to 1 if we're increasing so that we get a base bigger than 1, and then subtract it if we're decreasing so that we get a base smaller than 1. Okay, so let me try to show you with a few examples. A new car is purchased for $16,000, but its value is decreasing exponentially. After just 1 year, it is only worth $12,000. We want to estimate the car's value after 10 years. While I could make a list of these values and try to find the pattern and do it that way, writing an exponential function to model this would make it very simple. So, let's say I wanted to write an exponential function in this form, y equals a times b to the x power. X would be the independent variable here, which would be years. And then y would be the dependent variable, which would be the value. Sorry, I was looking for the word. There it is. Okay, so value. So if I want to write my exponential model, I need to know two things. I need to know what is the starting value and what is the growth factor. What am I multiplying by to go from one output to the next? So in this particular case, I know the starting value. Simple. They tell me that this car was purchased for $16,000. That's my A. And I can find B with division. I know my first output, the first value is 16,000, and I know the next one is 12,000. So imagine this, okay? Time 0, my car is worth $16,000. 1 year later, it's worth 12,000. Now maybe I can't tell what I'm multiplying by to go from 16,000 to 12,000, but I can just divide. So if I take 12,000 and divide it by 16,000, I'm going to figure out what B is. Now I'm hoping that's making sense, but let me just go back here real quick to my table. If I have two consecutive points, right, I can see that I am multiplying by 3 to go from 1 to 3, but if I couldn't, 3 divided by the 1 here would give me that same value of 3. So that's the concept. That's what I'm trying to apply here. And I think I just erased. Yep, sure did. Okay, so back to this. So if I take 12,000 and divide it by 16,000, that's just really going to be 12 over 16, which is going to be 0.75 or 3/4, maybe the decimal you like better. Either way. So I get 0.75 for my growth factor. That means if I start at 16,000 and multiply it by 0.75, I end up at 12,000 for the next year. And it should make sense that my base is less than 1 because the value of this car is decreasing. So my function becomes y equals 16,000 times 0.75 raised to the x power. So if I just said write a function, then we're golden, we're done. But the whole purpose of this was to try to estimate the value after 10 years. Well, that I can easily do now by inputting 10 in for my x. So we're going to say y is equal to 16,000 times 0.75 raised to the 10th power, and then the calculator is going to estimate this value for me. So we start at 16,000, and then we're only going to have 75% of the value every year after that. For 10 years, we end up at $901.02. $901.02 would be the estimated value based on the pattern of what's been happening in that function. And my work looks like all kinds of a hot mess there. Let me just move this. Hopefully what I did makes sense. In my head it did, but I'm looking at this work and it's like slop. Okay. Alright, so let's try another one. In the next example, it says in 2018 a couple bought their home for $250,000. Its value has grown by 4% each year since then. Estimate its value in 2025. So again, my goal would be to write a function and then use it to try to estimate the value. So a times b to the x power, where again I'm going to let x represent the years, and I'm going to let y represent the value, because the value is dependent on how many years this thing has been, sitting on the market or growing in value, or whatever it is, in this case growing in value. Okay, so a is my starting value, and that's given to me as $250,000. That's what they bought the house for. Now they're telling me here it's growing by 4%. So the house starts at 100% of its value, and it's going to gain 4% every year after that. So B should be 104%. But we don't actually use percents when we make calculations. We use the decimal for those percents. And so we're going to change this to 1.04, and that's what we're going to plug into our function. So our function becomes y equals 250,000 times 1.04 raised to the x power. And again, a base bigger than 1 should make sense. This thing is growing in value. Now we can go to the question, which says to estimate the value in 2025. Well, that would be 7 years after they bought their house. So I'm going to input a 7 in for x. So y is going to equal 250,000 times 1.04 to the 7th power. And calculator is going to tell us the estimated value. And there it is. So we'll say this is going to be about $328,982 and about 94 cents. Because it's money, rounding to the hundreds place would be appropriate each time. Okay, done. And one last one. I think if you're feeling okay with this, you try this out. Otherwise, let's get this done. So a stock opens up on the market for $40 a share. Since then, it's lost 2% of its value per month. Predict its value after a year. So again, we're trying to write our model. It's y equals a times b to the x power. X, again, let's be consistent with colors. X is going to be the time in months, because that's the rate at which we're losing value. It's per month. And then y is going to be the value. I need to know the starting value, the a, which it gives me. This stock opens up at 40 bucks a share. And then b. This time it's losing 2% of its value every year. So we start at 100% of the value. If we're going to lose 2% each year, we need to subtract 2% from the starting 100% value. That means our growth factor should be 98%. Every year, we're only going to have 98% of the value we had the year before. But 98% as a decimal, being 0.98, is what we're going to use for the value in the actual equation. Okay, so we write our function now as 40 times 0.98 to the x power. And now we go back and answer the question. So it says predict the value after a year. Remember, our x values were months, so that would be 12 months for a year. So I'm going to plug a 12 in for x. So y is going to equal 40 times 0.98 to the 12th power, and then calculator. So we start out at 40 bucks. Every year we have 98% of what we had the year before. After 12 years, we have $31 and 39 cents left. Not a humongous loss, but losing money is not great. Okay? So there's, just a few examples. I'm hoping some of this looks familiar. And just let me back up to this problem real quick here. Since I'm talking about growth factors, I just want to point out, since there's a 0.75 here, this is a problem that's losing 25% of its value. Hopefully that makes sense. Okay? So that growth factor, if we're given two consecutive outputs like we are here, we can always divide to find it. If we're given a percent gain or loss, we're going to add or subtract to 100. But just always keep in mind that base. If it's something that's growing in value, that base should be less than 1. If it's, what did I say? If it's growing in value, no, the base should be bigger than 1. If it's losing value, the base should be some fraction or decimal between 0 and 1. Okay, in worst case scenario, you could always just make a list of your values if you don't have to go too far with it. But hopefully the functions make sense. Okay, hopefully you got enough to get going on your homework. But as always, if you need any extra help, then reach out. Till next time, take care.